From Earth, each and every star seen with the unaided eye belongs to our galaxy, the Milky Way. This spiral galaxy contains hundreds of billions of stars. If we could travel out of the galaxy and look back, we would see that our Sun lies about 2/3 of the galaxy's radius away from the center. Measuring the positions of the stars in the galaxy and calculating their distance from Earth is complicated, because all the objects in the sky are constantly in motion. The Earth rotates about a slowly wobbling axis, whilst it orbits the Sun. The Sun itself wobbles slowly about the center of the solar system as a result of the gravitational pull of the planets. The Sun and all the other stars in the Milky Way move around the center of the galaxy in different orbits and therefore at different speeds. Incredibly, the Sun takes more than 200 million years to orbit the center of the Milky Way once.
So to measure the position of a star and its movement, astronomers need to know its right ascension and declination. In other words, its longitude and latitude on the celestial sphere. As well as these, 3 further parameters are required. One is distance, and the other 2 are associated with the star's motion on the celestial sphere.
The 3 stars famously known as Orion's belt. As these stars orbit the center of the galaxy, slowly, over time, their positions in the night sky change. This movement is known as the proper motion and is a result of a star's motion through space relative to the solar system. Due to the vast distances to the stars, the proper motion of a star measured over a period of 1 year is extremely small. It could take a star thousands of years to move through the apparent size of the moon on the night sky. Stars also move towards or away from an observer along their line of sight. This motion is known as a star's radial velocity and plays an important part in building a true picture of a star's movement in our galaxy.
With everything constantly in motion, how do astronomers measure the distance to the stars?
If the position of a star on the celestial sphere is observed over a period of 1 year, as the Earth orbits the Sun, the closest stars will appear to move against fixed, more distant background stars. This is the parallax. It is the only direct way to measure distances to celestial objects. Astronomers measure the position of a star from 2 points in the Earth's orbit with a known separation. This distance and the measured angular displacement with respect to the fixed background can then be used to calculate the distance to the star. Due to the concept of parallax, a star followed for a year appears to draw out a small circle against the background, which is actually due to the Earth's orbit around the Sun. The further away the star, the smaller the circle. This means that at some distance this circle will appear to be a point, and the parallax would be impossible to measure. For stars which are more than a few thousand light years away from Earth, the parallax angle becomes too small to be measured accurately by ground-based observatories. Therefore, astronomers have developed other indirect methods to find distances to celestial objects that depend heavily on theoretical models and assumptions.
The discipline of precisely measuring the positions of stars has a strong European heritage. Astrometry was pioneered long before the astronomical telescope existed. In ancient Greece, Hipparcos of Nicaea painstakingly made naked eye measurements of the positions of the stars and planets, producing the first catalogue of just over 1,000 stars. Over the centuries, many astronomers, including Tycho Brahe, John Flamsteed, and Otto Struve, continued this task with ever-advancing technology. Accurate measurement of star positions from the surface of the Earth is a difficult task. Positions can only be measured relative to other stars that can be seen, and only within a small portion of the sky. In addition, the Earth's atmosphere distorts the stellar images to some degree, thereby limiting the accuracy with which their location can be defined. The biggest advancement in mapping the stars came late in the 20th century, 40 years after the beginning of the space age. In 1989, Europe launched the first spacecraft to chart the positions of the stars. During a mission lasting just over 3 years, Hipparcos mapped over 100,000 stars with very high accuracy. This provided astronomers with a three-dimensional picture of the distances and movements of stars in the vicinity of the Sun. The wealth of data collected by Hipparcos is still being used by astronomers all over the world, more than 15 years after the satellite ceased to operate. When measuring the positions of stars, a huge amount of information is collected. This information is extremely important in all disciplines of astronomy, such as studies of the solar system, stellar structure and evolution, the Milky Way, cosmology, and even general relativity. Let's have a look at a few examples.
With information collected by the Hipparcos mission, astronomers were able to determine that the Milky Way is changing shape and identified that billions of years ago our galaxy swallowed a small, neighboring galaxy as it passed too close. Amongst other numerous results, data produced by this mission helped astronomers to predict when comet Shoemaker-Levy 9 would collide with Jupiter in 1994, and confirmed Einstein's prediction that gravity bends light. Catalogs of star positions are routinely used to point ground-based telescopes, navigate space missions, and drive planetaria. Information from Hipparcos has enabled astronomers to trace the Sun's passage through the galaxy back in time. This has shown that over the last 500 million years, the Sun has passed through 4 of the Milky Way's spiral arms. The times that these traverses occurred appear to coincide with extended cold periods on Earth. Perhaps the densely filled star and gas environment of the spiral arms have an effect on the Earth's climate. Mapping the positions and motions of stars allows astronomers to develop a frame of reference, which in turn means that comparisons can be made between measurements of the same object taken at different times, at different locations, and in different wavelengths. Astrometry measurements are instrumental for timekeeping. Universal time is calculated by synchronizing atomic time to the Earth's rotation. Measuring star positions allows a frame of reference to be developed, so as more accurate positions can be achieved, a better measure of the Earth's rotation can be determined. In combination with other data, many other physical properties of a star can be determined from astrometric data, such as the luminosity, radius, mass, and age. This information is then used to understand the internal structure and can lead to even deeper explanations of stellar and galactic evolution. Accurate data about the distances of stars, combined with models of stellar evolution, are used to find stars that are like our Sun now. These solar twins are targets in the hunt for exoplanets which may harbor life.
This is